Alright, lesson 24. Make sure you have that lesson out in front of you, please. Alright, so we are going to be looking at prove the Pythagorean theorem using similarity. Alright, so let's go ahead and look at the opening exercise. It says, find the length of the hypotenuse of a right triangle whose legs have the length of 50 and 100. Alright, so let's stop for just a second. Let's go back to this for just a moment. Alright, so I want to show you this figure right here. Alright, let me scan in just a little bit so that you can see that diagram. Alright, so what if I wanted to figure out what C was? Alright, how would I figure out C? Well, normally what I would do is if I know X and I know Y, then I could add them together to get X plus Y is equal to C. Alright, so remember we said that when we have an altitude, it divides our right triangle into three similar triangles. Alright, now so we have three similar triangles here. So we know in this case that triangle ACB is similar to triangle ADC is similar to triangle CDB. Alright? So I know those three triangles are similar. Alright. So our goal is to prove that the Pythagorean theorem using what we know about similar triangles. Alright, so let's look at, and I'm going to do some drawing here. Let me zoom back out. Let's consider a right triangle here. Alright, so let's say I have this right triangle. A, B, C. Here's my right angle. And then I've got these sides. Okay? So our goal is to prove the Pythagorean theorem. Consider the right triangle, triangle ABC. So that angle C is the right angle. We label the sides lengths A, B, and C so that the side length A is opposite of angle A, the side length B is opposite of angle B, and the hypotenuse C is opposite angle C. Alright, so that's why I labeled it the way I did. So next we're going to draw the altitude from the right angle to the hypotenuse so that it splits the hypotenuse at a point D. Alright, so let's draw our altitude. Alright, and mine's not going to be perfect, but we know an altitude is a perpendicular segment, and it said that it divides, it splits the hypotenuse at point D. Alright, and we're going to say that this is lengths X and Y. Alright, so in order to find C, I would do X plus Y would equal C. Alright, and this is exactly what we were just talking about. So what do we know about the original triangle and the two sub-triangles? Well, we know that these three triangles are all similar. Alright, so I can rewrite them as three similar triangles. If you want me to, we can draw them out. Let's do that. Let's look at our our original triangle and our three sub-triangles. So I have triangle ADC, alright, and with D being, so ADC, this triangle here, D is our right angle, so this is Y, this is B, and this is H. All I'm doing is taking everything from this figure and just redrawing it. Alright, so then I have my original triangle, alright, and that was ACB, with C being our right angle. And so this was B, this was C, this was A. Alright, and then I have my second subtriangle. Alright, which would be triangle CDB, with D being my right angle. So this was H, this was A, and this was X. So all I did was I took this figure here and I divided it into the three similar triangles. So we want to prove the Pythagorean theorem using what we know about similar triangles and the ratios that we wrote in lesson 23, which we kind of really didn't talk about a whole lot. But if you remember, let's think about going back to lesson 23, we had some ratios that we could look at based on similar triangles. Alright? And I was looking for all of those so that I could write them. But we did shorter leg to a hypotenuse. We can look at the longer leg to the hypotenuse. Or we can look at the shorter leg to the longer leg. And we kind of used this a little bit in the lesson where we were looking at similar triangles. Alright? So these are some of the ratios that we used when we were doing our similar triangle lesson. Alright, so we begin by identifying the two triangles that have each angle B as one of their angles. Well, these two triangles here have angle B as their triangles. The triangles are ABC and CBD. Since they're similar, we can write equivalent ratios of the two similar triangles we just named in terms of the longer leg and the hypotenuse. Alright, so let's look at our longer leg, and that is X and A. So we will do, we can put this one over top of this one. So we'll do A over C as our hypotenuse is equal to X over A. So here we're doing longer leg to hypotenuse. And it doesn't matter if I'm doing which one goes on each side of the equal sign. In this case, this is my longer leg, this is my hypotenuse. Alright? So now we solve. We cross multiply and we get A squared is equal to XC or CX. Alright? Now we're going to identify two right triangles in the figure that each have angle A as our acute angle. Those two triangles are ADC and ACB. Alright, so we can write equivalent ratios in terms of the shorter leg to the hypotenuse. Alright, so with that being said, let's go ahead and write our thing here. So my shorter leg is H and A. No, I'm sorry. I was looking at the longer leg. Y and B. Alright, so once again, doesn't matter which way I do it. So I can do Y over B is equal to, now since I started with this one, I need to do my hypotenuse, and that would be B over C. Cross multiply, I get B squared is equal to YC. Alright? Our goal is to show that A squared plus B squared is equal to C squared. That is our Pythagorean theorem. So we know that A squared is equal to XC, and we know that B squared is equal to YC. So by substitution, let's look and see what we get. Alright, so our goal is to prove a squared plus b squared is equal to c squared. Alright, so I know that by substitution, I get xc and I get yc is equal to something. Okay? So let's look at this. I can pull a c out. I get x plus y. Alright. X plus y is a c. So I have c times c, which is c squared. Alright, so I have a squared plus b squared equals c squared. And we've proven the Pythagorean theorem using similarity. Alright, so next we need to show that the converse of the Pythagorean theorem is true. Alright, so we're going to be looking at the converse. If you remember, converse is the opposite. Alright, so the converse of the Pythagorean theorem, if a triangle has the sides lengths a, b, and c, so that a squared plus b squared is equal to c squared, then the triangle is a right triangle with c as the length of the hypotenuse. Alright, so let's look at my triangle again. Alright, so I have triangle ACB. This time I don't know if it's a right angle because I'm trying to prove it's a right triangle. We've constructed a right triangle even though we're not marking it. Okay? So now, consider the right triangle with legs lengths of A and B. By the Pythagorean theorem, we know that a squared plus b squared is equal to c squared. Taking the square root of both sides gives us the length of the hypotenuse as c. Alright? So, I can use this to prove that if I can do a squared plus b squared plus c squared, then I have a right triangle. Alright, so let's go ahead and look at our exercises. So find the length of the hypotenuse of a right triangle whose legs have the length 50 and 100. Alright, so I'm trying to find my hypotenuse, my c squared. So I'm going to do 50 squared plus 100 squared. Alright, so 50 squared is 2,500. 100 squared is 10,000. So I get c squared is equal to 12,500. In order to get rid of the square of a number or square of a variable or a number, I take the square root of that. So c is equal to the square root of 12,500. All right. So I can split this into the square root, let me come over here, of 2 times 2 times 5 times 5 times 5 times 5 times 5. Okay? So I can look at this as the square root of 2 squared times 5 to the 5th. Well, we know that 2 squared, the square root of that would be 2. 5 to the 5th I can rewrite as 5 to the 4th and 5 to the 4th times 5. The square root of 5 to the 4th is 5 squared. And then I have the square root of 5 left. So go ahead and multiply this out. 5 squared is 25 times 2 is 50 square root of 5. Alright? Can you think of a simpler method of finding the length of the hypotenuse, for example, number 1? So, can I think of something simpler? Really, if you can come up with something simpler, write it down. You might know something about similar triangles and the scale factor, but just if you know something simpler, go ahead and write that down. We're not going to spend all the time talking about every way that we can make this simpler. Alright, let's look at example number 3. Find the length of the hypotenuse of a right triangle whose legs have the length of 75 and 225. Okay. So you can think about similar triangles. Alright? If I think about similar triangles, then it might help me to make this a little bit easier. So a right triangle with legs of 75 and 225 have leg lengths that are 75 times longer than a triangle with the leg of 1 and 3. Alright? So think about this. 75 times 1 is 75. And then 75 times 3 is 225. Alright? So I can look at this and say, okay, well, let's talk about what I know about a right triangle with legs 1 and 3. Alright, so that would be 1 squared plus 3 squared is equal to c squared. I get 1 plus 9 is equal to c squared. So c would equal the square root of 10. So the hypotenuse of my triangle would be square root of 10. Alright. So this right triangle has legs that are 75 times longer than a triangle with leg lengths of 1 and 3. Which has a hypotenuse of the square root of 10. Okay? So now, what can I do? So I know that the length of the hypotenuse, since my legs are 75 times longer, then my hypotenuse has to be 75 times longer. So my hypotenuse is going to be 75 times the square root of 10, or 75 square root of 10. Okay? Alright, exploratory challenge. An equilateral triangle has sides of lengths 2 and angle measures of 60. As shown below, the altitude from one vertex to the opposite side divides the triangle into 2 right triangles. Are those triangles congruent? Explain. Alright, so let's look at this. Are they congruent? Well, I know I have a side that is equal. I know I have an angle that is equal. Any other way I can prove these triangles congruent? Guys, look at this. By reflexive property, I know that side has to be congruent also. So the triangles are congruent by angle, side, angle. Okay? Since the altitude is perpendicular to the base, then each of the right angles has an angle that measures 90 and a 60, which I actually did. We can't do side-side angle, so I've got to go back and I messed up just a minute. So 90 and 60, so that means this has to be 30. So now I have my angle side angle. Alright? What is the length of the shorter leg of each of the right triangles, and explain? Well, since the total length of the base of the equilateral triangle is 2, alright, because remember it says it is an equilateral triangle, that means this is 2. The two right angles formed are congruent, then the bases of each must be equal in length. So therefore, the base of one right triangle is 1. This is my shorter leg. So since it is an equilateral triangle, the third side must be 2. Since the two subtriangles are congruent, then the shorter side must be 2 divided by 2, which is 1. Okay? Use the Pythagorean theorem to determine the length of the altitude. So I've got 1 and I've got 1. So pay very close attention to what you do here though, because now I've got a side and my hypotenuse. So I've got 1 squared plus, I don't know what the other side is, and then my hypotenuse. So I have 1 plus x squared is equal to 4. Subtract 1, x squared is equal to 3. So x would be equal to the square root of 3. So the other side has a length of square root of 3. Write a ratio that represents the shorter leg to the hypotenuse. Alright, well the shorter leg is 1 and the hypotenuse is 2. Alright. Write a ratio that represents the longer leg, which we just figured out was the square root of 3, to the hypotenuse, which is 2. And write a ratio that represents the shorter leg to the longer leg. The shorter leg was 1. The longer leg was the square root of 3. By the AA criterion, any triangle that measures 30, 60, 90 will be similar to this triangle. If a 30, 60, 90 triangle has a hypotenuse length of 16, what are the lengths of its legs? Alright, so it's telling me that if any triangle that has measures of angles 30, 60, and 90, they're all going to be similar. So if the triangle has a hypotenuse length of 16, what are the lengths of its legs? Alright, so look at this triangle here. We don't know what the shorter leg is, so we're going to let A represent the shorter leg. Alright, so now I've gotten a, let's look at what I have. Alright, I know that it has a hypotenuse of 16. Alright, so I need to do something that represents the shorter leg to the hypotenuse. Well, we did a shorter leg to the hypotenuse ratio here. So what we know is our shorter leg to our hypotenuse is equal to we're trying to find the shorter leg here, and the hypotenuse is here. Alright, so cross multiply, I get 16 is equal to 2a. Divide by 2, so my shorter leg here would be 8. Alright, let B represent the longer leg. Alright, I know my hypotenuse. My ratio for my longer leg to the hypotenuse is the square root of 3 over 2. So then my longer leg over the hypotenuse. So go ahead and let's do this. Multiply. So I get 2b is equal to 16 square root of 3. I divide b by 2, so b would be 8 square root of 3. So the lengths of my triangle with a hypotenuse of 16 is 8 and 8 square root of 3. Alright? An isosceles right triangle has leg lengths of 1, as shown. What are the measures of the other two angles? And explain. Well, what do we know about the base angles of an isosceles triangle? They have to be equal. Alright? So the base angles of an isosceles triangle are equal. I know I've got a 90-degree angle, so that leaves me 90 left. So if I divide 90 by 2, that means both angles have to be 45 degrees. Alright? So, guys, we are learning about these types of triangles, a 30, 60, 90-degree triangle. Alright? Now we are looking at a 45, 45, 90-degree triangle. Use the Pythagorean theorem to determine the length of the hypotenuse of the right triangle. Well, if both sides are 1, so I have 1 squared plus 1 squared is equal to c squared. 1 plus 1 is equal to c squared. 2 is equal to c squared. Square root of that would be the square root of 2, so my hypotenuse is the square root of 2. Alright? Is it necessary to write all three ratios, a shorter leg to hypotenuse, longer leg to hypotenuse, and shorter leg to longer leg? It's not necessary to write all three ratios. The reason is that the shorter leg and the longer leg are the same length. Therefore, the ratios will be the same. Alright, so it's not necessary since the longer leg and shorter leg are equal. The shorter leg to hypotenuse and longer leg to hypotenuse will be the same ratio. Okay? Write a ratio that represents the leg to the hypotenuse. Well, leg is 1, hypotenuse is the square root of 2. So by the angle criterion, any triangle with the measure of 45, 45, 90 will be similar to this triangle. So if a 45, 45, 90 triangle has a hypotenuse length of 20, what are the lengths of the legs? Alright, well, since they are the same ratio, I only have to do it one time. So my leg to my hypotenuse is equal to my leg to my hypotenuse multiply square root of 2a is equal to 20. Alright, so divide by the square root of 2. So A is equal to 20 square root of, over the square root of 2. Remember, in order to do this, I've got to multiply by the square root of 2. So I get A is equal to 20 square root of 2 over 2, which is equal to 10 the square root of 2. Alright? Alright guys, I am slowly bringing you into trigonometry, so this is a lot of work. Have a great week.